Hi everyone. So we're just going to do a quick YouTube video just going over how to process the data for our Claussius Clapeyron lab. So what I have up here, all I've done is just put in data that I've collected in past semesters, so it might be a little bit different than yours, just based on whatever the temperature and pressure was in the room. So you can see I have my columns for volume and temperature already filled in. What I'm looking for you guys to do is to organize your data so all the columns are clearly labeled and also have correct corresponding units as well. So what I'm going to teach you guys to do is how to use Excel to do many of the mathematical functions that make using Excel essentially easier than trying to do all of this out by hand. Right? We've already seen a couple of these done in lab, so we know a lot of calculations can be done really quickly using Excel. All right. And just a heads up too, part of the grade for this worksheet is filling in and sending this Excel sheet to me, but I'm going to be checking to make sure you're using all the correct Excel functions rather than just doing everything out by hand, because I know you guys can do that. Right, so why don't we start off, we did this in class first. The first thing we're going to do is automatically correct our volume for that upside down meniscus. So if we remember to tell Excel to do, it's ready to do math rather than just type words, we click on the cell we want, we hit equals, that's going to tell us that we're doing mathematical operations. So we click on the cell that has the corresponding volume that needs to be corrected, and we need to subtract zero point 0.2 milliliters, so we can see it's already done for us. If we click on the cell, we see it turns the cursor into a plus sign, and if we move that down to the bottom right hand corner, we can click, drag, and then all of the corrected volumes have been done for us. The next thing we're going to need to do is convert this from milliliters to liters, just to make sure things are in the correct units, so when we use our R value, all of the units are going to cancel out appropriately. So we take our 7.6 milliliters, and if we divide that by 1,000, we should get that in liters. We'll do the same thing. We click on the cell, go to the right-hand bottom corner, click, and drag. Good, so those are our easy ones. Another easy thing to take care of right away would just be converting our temperatures from Celsius into Kelvin. And so the way we're going to do that is we're going to hit equal, click on the cell that we want to add 273.15 to, so then we do plus 273.15, click on the cell, go to the right-hand corner, drag down. Everything's automatically calculated. All right, so that's the easy stuff. Now we're going to learn a couple of more tricky tips that are actually really, really helpful. And by tricky, it's a little bit harder than just click equals and drag down. So we did the example in class to figure out the partial pressure inside the bubble, inside the graduated cylinder, how to calculate that using PV equals nRT. Right? And we had to do it in two distinct steps. The first thing we need to find out is the number of moles of air that are in the bubble, and then we need to figure out the number of moles, or the partial pressure, sorry, due to air at each data point. So let's start down here first. Right? So what I've done, I've just typed in the atmospheric pressure of the lab. It might be 1.009 for you guys. The day that I recorded this data, that's the pressure that was in the lab, so that's what I'm going to use. You recorded in inches mercury, so make sure you convert that to atmospheres first. All I did was go ahead and write down the units for R. Excuse me. The big thing to remember here, you can see I've only typed the number and I wrote the units next to it. Excel gets really confused if you put in numbers and units together. It will just treat it as a word and will be unable to do mathematical operations on it. So I did the same thing for R. You can see up here it's just a number, and then I keep the units in the cell next to it. So if we're going to solve for the moles of air, right, we need to do this at our coldest temperature, right? So that would be, in this case, 5 degrees Celsius. The reason for that, we're making our assumption that all the pressure that's inside the bubble trapped within the graduated cylinder at this point is only due to air, because the vapor pressure of water should be 0, or at least that's our assumption. It might be a little bit easy if you write down PV equals nRT so you can follow what I'm doing, but I rearranged the equation so that I'm solving for moles of air, so it should be N equals P times V divided by R times T. So if we do that, the way I tackle this first is we're just going to do the numerator first, and then we'll do the denominator. So we do equals, so we're telling Excel to do our calculations, open parentheses, so it's going to follow our orders of operation. So if we need to do a number of moles, so we already made the assumption that since all the pressure is due to air inside the bubble, right, it means the pressure inside that bubble, because it's an open container, is equal to atmospheric pressure. So there's our P, and we click on the cell that has our atmospheric pressure. We'll multiply it by the volume at our coldest temperature. So there's our corrected volume, and that's the volume of our air bubble. And we'll close parentheses, because that's the top of the numerator. That's P times V. We'll divide by open parentheses R times the absolute temperature of our coldest value. We do that, and that's the number of moles that are found, moles of air in our bubble, in our graduated cylinder. Good. So the next thing we need to do is then determine how much pressure is due to the air at every data point, right? So when we're down here, our last data point down here, this one should equal atmospheric pressure if we've done our calculations correctly. But we said as the water gets warmer and warmer, more of the total pressure is going to be due to the amount of water vapor going into the vapor phase and increasing the volume of the gas bubble. So let's do this. We'll start at the top and we're going to drag down. So what we're doing now is we're rearranging PV equals nRT so that P equals, so the pressure due to the air is equal to the number of moles of air times R times T divided by the volume of the air bubble. So if we want to do that, we say equals times the number of moles of air times R times the temperature for this data point in absolute temperature, right? So since that's going to be the numerator, we need to put all of that in parentheses, and then we'll divide by the volume, the corrected volume. So that should give us the pressure due to air at that particular data point. The rest of it's going to be due to the water vapor, right? So that means we know it's going to be equal to, because the law of partial pressure means the pressure due to the air plus the pressure due to the water vapor has to equal to the atmospheric pressure because it's an open system. So we know that's going to be the atmospheric pressure minus the pressure of the air has to be then due to the pressure of water. So these two numbers add up to our total pressure. So let's pause for just a quick second. We're going to see something, we're going to do something wrong on purpose, and then we're going to go back and try to fix to make our lives easier. So if we try doing the click on the right hand corner and drag it down, we're going to get all these numbers. This makes no sense, right? So let's take a look at what Excel did. Here everything makes sense, right? There's my moles of air, there's my R, there's my absolute temperature, and there's my corrected volume, right? That makes all good sense. We take a look at this cell now. When I dragged it down, what ends up happening is, since we drag those cells down, it drags down all the other cells that it thinks it needs to calculate. So now it has an empty cell where it used to be moles of air is now empty. So there we have our 0, and so everything gets multiplied by 0. And if we keep following those, we'll see we're just grabbing cells that have nothing in it. So we got to find a way that will basically lock these cells in our equation. And the way we do that, we take a look, we said, okay, the moles of air never change in any of these in these cells. So the way we're going to lock that number in is we put a $sign before the letter and a $sign before the number. What that does now is tells Excel that we'll always use this cell for the first part of the equation. And we do the same thing for R, because R is not going to change. So there's our two $signs, one in front of the letter, one in front of the number. Hit enter, and now let's see what happens when it drags it down. Oh look, everything worked out. Right? We still want to make sure that the corrected volume and the absolute temperature changes as each data point changes, so those shouldn't be locked, but we never changed the amount of moles of air and never changed the value for R. So good. So we've learned how to lock cells that we don't want to change and allow other cells to change that we do want to change as we drag down our formula. So let's do the same thing here. We know we need to lock in the atmospheric pressure because that is not going to change, but we need to constantly keep subtracting the changing pressure due to the air. So we put in our dollar signs for locking in the pressure of air, click, and drag. Great. We notice we're going to have some negative numbers here. These are going to, it doesn't make sense to have negative pressure. That means at the time our data, the way we recorded it, because it's becoming harder and harder to accurately measure the volume changes. So you see here, all the volume changes hovered at 3.8, 3.8, 3.8, right, while the temperature was changing. So what that ends up doing is, because the temperature is slightly changing, the volume of air is slightly changing, pressure from the air is slightly changing. So it allows sometimes to get negative values. We're going to toss those out later, but for right now, we are not going to worry about them. According to the lab manual, we need to convert atmospheres to torr. So the way we're going to do that is take our atmospheres and use our conversion factor. So multiply it by 760. And now we're in units of torr. Great. If we look in the lab manual, what we need to do is we need to have an x-axis and a y-axis. The x-axis is going to be the reciprocal absolute temperature, and the y-axis should be the natural log or the partial pressure of water. So the way we want to do that is absolute temperature is easy. We just say equals 1 divided by, and we click on the absolute temperature for that data point. Good. Click, drag down. To do the natural log of the partial pressure of water, we hit equals and type in just ln, and it will give you a list of functions. You don't have to click on it. You could if you want. The way you want to activate it is you just open up the parentheses. Now Excel knows you're doing the natural log. Click on the number you want to do the natural log of, close parentheses, and there we go. And if you're ever unsure, you can always double check with a calculator. So this is what I was mentioning before. When we had these negative numbers, we knew this was going to be an issue, and this pound sign number is just telling you divide it by 0, or you did an operation that has no physical meaning. So we can graph it. Let's just delete them. All right. So we actually had to throw out 3 data points. So we take a look here. I've already made a graph, but let's go back. We can always just put in a new graph in case anyone doesn't remember how to do that. So we highlighted X is always first, Y is always second. That's how Excel does it. We'll go to Insert. We'll put in a scatter chart. There we go. So you can see we have a lot of white space, and we also have grid lines. So remind you guys again, never give me a graph with grid lines. I always want them deleted. We see here we have a bunch of white space, so the way we'll get rid of that, let's say, we'll probably just focus on this little area down here. So why don't we make our graph from 0025 to 004. So we'll change our bounds to 0.0025, and we'll keep it at 0024. Oh, sorry, 0004. Right? What's this guy doing? He's hanging out. We have 0.28. What we'll do, so some of these ones, especially when you get to the lower data points, because it's so hard to see that volume change, but the temperature constantly keeps changing, we're introducing a lot of error. So what I'm going to do is I'm going to get rid of these last 2 data points from the data set, because we can easily visually see that they're not following the trend. So the way you want to do that is you just click on the data points. That's what I did. It highlights where the data came from. We go to the middle. Sometimes you get lucky and you can get both at once. But all I did was drag up the y-axis, and then you drag up the x-axis. It's going, come on, right? And what it does is it just removes those points from the graph. And so we can even hone this in a little bit better. Let's go to, come on, there we go, 0.0028. Right, there we go. We can make the most use of our graph. We want to add a trend line, so we'll right-click, add trend line. Set equation, set r squared. Good. So I'm not going to go through everything on how to modify the graph, but remember you're going to need to label your x-axis and y-axes. When you're putting it into a figure, if it was a lab report, you want to get rid of the title, right? So you want to make sure the only thing we're missing right here is basically labeled x and y axes with units. So we take a look here. Here is our linear regression we know if we look at follows the Clausius-Clapeyron equation where we have y equals mx plus b, and I'm going to leave it up to you guys to figure out how to calculate delta HVAP from this information here. You have everything you need to know other than using the universal gas constant. So just remember for this one, I'm going to give you the heads up, when you're using your y equals mx plus b, you'll be using the 8.314 joules per mole Kelvin version of the universal gas constant. All right, hopefully that was pretty straightforward. Always, do a good job, try on your own, give it a good effort. If you're still having issues with this, we can definitely talk next week. But definitely, everything you should be able to do. I just want to see good effort, but if you're still getting confused, we can definitely talk more. All right.